So our next speaker is a member of Alpha Kappa Alpha, the sorority incorporated. I'm not sure what the incorporated part is, but it's the same sorority as our Vice President-elect Kamala Harris. So everyone, please welcome Kimberly.
All right. Hello, everyone. And thank you to the organizers for inviting me to speak to you today. As you may wonder, what could possibly be the connection between my talk and Snoop Dogg, of all things? But as you can see, the topic for my presentation today is analyzing count data, expressing data dispersion. And as you can see, this is done through my joint partnership at Georgetown University and the Census Bureau. Okay, so notice Snoop Dogg was counting 1, 2, 3, and to the 4. So he too can appreciate count data. All right, so for context with regard to regression analysis, of course, we're all too familiar with the idea of this being a fundamental means by which to establish the relationship between associated variables. For example, with the Census Bureau, one could ask about change in geographic units with regard to housing growth or decline. So if we're interested in the number of new homes in a region, then obviously most neighborhoods are stable, right? So you would not expect there to be any new homes in that area, and that influences the ideology of considering a zero inflated count model. And so with that in mind, of course, there are various models that are already in existence and popular in use. With the ZIP model, or the zero inflated Poisson, that underlies a Poisson distribution, which assumes equi-dispersion in the data, which means that the mean and variance equal. If we allow for over-dispersion, if we allow for over-dispersion, then a zero inflated negative binomial is popular. More broadly, for cases of where over-dispersion, I should say, implies that the variance is larger than the mean in a data set. More broadly, if we consider over or under dispersion, where with under dispersion, the variance is smaller than the mean, then one such choice to allow for such flexibility would be through a zero inflated generalized Poisson distribution. However, it's worth noting that this model can express some peculiarities and issues under certain conditions. And so it promotes the idea of me introducing yet another alternative flexible model for count data, namely the zero inflated Conway-Maxwell-Poisson. To offer some background with regard to the CMP distribution, as you can see, it's based on a 2-parameter count model that generalizes the Poisson as a special case. The lambda parameter here serves as a generalization of the Poisson rate parameter, and while the nu parameter serves as a dispersion parameter. So for this value nu, and this z function serves as our normalizing constant. It's important to note that when nu equals 1, this simplifies to our Poisson model, where, as I said, the nu captures the dispersion in the data. So if nu is less than 1, then it captures over dispersion. For nu greater than 1, it captures under dispersion. What's nice about this distribution is that it not only captures the Poisson distribution as a special case, but 2 other classical distributions as well. When nu equals 0, it captures the geometric distribution, again, where lambda is constrained to be less than 1 now. And when nu goes to infinity, it captures the Bernoulli distribution with success probability lambda over 1 plus lambda. When we think about a regression model underlying this distribution, the parameterization that I'll be working with here is that which originated by the original Conway and Maxwell paper and was revived in the Shmueli et al. Paper referenced above. However, there are other parameterizations that exist, and the interested reader can access my WIRES review paper with a student of mine, Bailey Premu. One of the nice properties of a CMP distribution, though, is that it has an exponential family form where I present the log likelihood to you here, such that we have the ability to recognize the joint sufficient statistics for lambda and nu. And as you may recall from your statistics training, this exponential family form allows for a lot of nice statistical properties to exist for this distribution. Some other properties include the ability to, or a representation for the moment generating function and a form for its moments, where, as you can see here, even just focusing on the mean and variance, that form is not of a closed form because of its dependence on that z function, that infinite summation that I presented to you earlier. As such, where I present the representations for the mean and variance, they do have approximations that exist, where those approximations hold for the cases where the data are either over dispersed, hence nu is less than or equal to 1, or lambda is sufficiently small. Moving forward to thinking of a regression model, then we now have this framework where we consider the log linear relationship between lambda and our covariates. Now, what's important to note here is that lambda is not necessarily the mean, except for the case of the Poisson model. And so more broadly, what we're looking at is a nonlinear functional relationship between, if you will, the mean of the data and the covariates. However, in the Sellers and Schmele paper, we stand by the use of this relationship because it allows us to clearly recognize the generalization that's attained from the special cases to this broader CMP. Again, for the case where nu equals 1, we are considering the case of a Poisson model, in which case this log lambda relationship is precisely the usual or typical relationship that we consider for our rate parameter. As well, I remind you that another special case was the Bernoulli distribution when nu went to infinity. Here, the underlying logistic model then is likewise captured. If we move forward to consideration, of a zero inflated CMP, then the idea now is that we are incorporating a generating process that allows for excess zeros. So with the underlying CMP model as our motivation, as you can see, we incorporate a third parameter, P, to consider the probability of having extra zeros in the data. And so we can write out the formulation for this zero inflated CMP model now, where now that we're going to broaden the scope to consider a regression analysis for it, we are again allowing, a log linear relationship for lambda and nu respectively, and meanwhile, a logistic model for P. So that said, it's worth noting that the zero inflated CMP, of course, captures the analogous special cases, as did the original Conway-Maxwell-Poisson. So for nu equal to 1, we recognize that we capture the zip model, or the zero inflated Poisson. When nu equals 0 and lambda is less than 1, we capture a zero inflated geometric regression. And if you think through our special cases, remember when nu went to infinity, we captured the Bernoulli. So one would imply that this is a capturing of a zero inflated logistic model. Well, what does that mean here? Because of course, in a logistic, the response values are either zeros or ones. Well, all that means now is that we maintain a logistic framework, yet we adjust in our success probability for P of having more zeros. So with all of this in mind, and presuming the log linear relationships for lambda and nu and the logit for the P, the question now becomes how to estimate the corresponding coefficient values in those models. And we suggest doing so through the method of maximum likelihood estimation. And where here, because of the complex nature of the underlying score equations, one has to do this numerically, hence the need for R. And so we can perform optimization procedures such as the bounded nonlinear minimization, or the direct nonlinear minimization, or simply a general optimization form, where in all of these cases, it's recognized that the function of interest is to be minimized. And hence, the function that one would supply would actually be the negated log likelihood form of the function of interest. And with this optimization, the advised starting parameters or starting values would be those values with which, say, we consider under a Poisson model. So be it either regular Poisson regression or the zero inflated analog, depending on your model of interest. And so with those starting values in place, then the optimization procedure can occur and we can obtain our estimates. And meanwhile, we can maintain the form of the underlying Hessian to establish our Fisher information matrix and thus obtain our standard errors. Next, with all of this in mind, a popular question that usually arises is how to perform a test to assess for the existence of potential significant dispersion in the data. And so a natural approach here would be to consider a likelihood ratio test, since much of the information is already contained under the hood, if you will, within our regression object. And of course, we remember that under the proper regularity conditions, the transformed likelihood ratio test statistic has a chi-squared distribution with 1 degree of freedom. Alternative, we can perform parametric bootstrapping as a means by which to conduct our test as well. Meanwhile, it's also worth noting, if one is interested in one of the other special cases, say the geometric or the Bernoulli, just recognize that since nu is in the boundary in those conditions, we have to consider a chi-squared mixture for those instances. So with all of this in mind, my package Comp-Poisson Reg is available on CRAN and can handle everything that's been discussed here. So it can fit the CMP or its zero inflated analog model to data. And it can provide one with estimates, perform hypothesis testing or model diagnostics. It can handle constant or variable dispersion. And to illustrate this model, and the R package, excuse me, I provide us with the following illustration with regard to maternal health and mortality data. And so here we are considering an example where we have collected data across various provinces in the Dominican Republic, and we're interested in understanding various aspects about maternal health and birth outcomes. And so as you can see here, we pulled the data from online regarding information such as the number of deaths across these different provinces, and variables such as the number of beds, the number of vaginal or C-section births respectively, the number of abortions, etc. And so the idea is to consider an association between the number of deaths that have occurred in each of the provinces versus some measure regarding these various explanatory variables. Okay, and of course we're going to do this using, since we're assuming or find in the data that there don't seem to present any excess zeros in this data set, we simply went with the basic CMP regression for illustration. All right, so what we see here is the call glm.cmp is the functional call to perform a CMP regression, where the usual formula is as one would always expect, where we have the response tilde the explanatory variable of interest. And here we're just running I'll illustrate a simple regression to associate the number of deaths with the number of beds. And so when we run a summary of the model output, you get what you would expect, namely, and I should be clear, the output is stretched over this and the next slide, where what's initially presented is of course, the natural coefficient table that exists for the coefficients associated with lambda and that associated with nu here. And so, as you'd expect, we have the corresponding estimates, standard errors, z-values, and p-values. In particular, I focus your attention on that p-value for the, if you will, the gamma term that associates with new. We notice that it's statistically significant here, and that is reiterated in the output directing us with regard to new. So we have a direct estimate for the constant dispersion new. Notice it appears to be statistically significantly less than 1. In fact, it's on the closer end to 0 here. And we provide the corresponding standard error. More output, as you see, which is presented, includes the sample size, various information criteria, and convergence information. Focusing our attention on the AIC and BIC, we'll touch on this later. But it's important to note that because the data set was over-dispersed, one of the reasons that this can happen, here I'm just pointing out that the optimization did in fact converge. One of the reasons for over-dispersion is that the model may not be complete enough. In other words, we should consider more variables in our model. Doing that here, we find that the coefficient table now presents an output where the gamma parameter is not statistically significantly different from 0. And what this implies is that the value for new is not statistically significantly different from 1. What does this mean for us here? That under this fuller model, we have something that can be achieved apparently with Poisson regression. And that is more settling when we look at the information criteria and recognize that the AIC and BIC values have now been reduced, which is what we would hope for a more optimal or preferential model. And so with this information in place, we can now make the informed decision to consider, for completeness, I'm noting that the optimization did in fact converge again. But now for completeness and more precision in our estimation, we can now go to the usual GLM and conduct our Poisson regression accordingly. And so now when we run it, what we're obtaining is more information with regard to the usual suspects. We have our coefficient table, we can look at statistical significance, we have more refined measures of the estimates in place here for understanding. And with that said, because I have now reduced my model consideration to the Poisson, I have reduced the associated AIC accordingly because I've removed the extra dispersion parameter. So while this is an illustration, and the analysis is deserving of more study, one of the points of note here that came of it was the question of potential incorporation of offsets into the model. And the current form of the Poisson reg does not allow for that. And so this is ongoing work that's in place now to try and incorporate offsets. So in conclusion, I hope you've learned that the ZI-CMP serves as a powerful regression, if not for explanation, but also for generalization should you have over or under dispersed data, particularly under dispersed data. It contains common regressions, and the Poisson reg package is a very helpful tool for addressing this matter. More work that has since been done with regard to regression further expands to what I call a zero-inflated sum of CMPs, which contains a zero-inflated binomial, Poisson, and negative binomial as special cases. The CMP my work in the CMP does not stop here. It spreads onward to work in control charts, distribution theory, etc., as you can see here, a wide array of methodological developments. And so in closing and recognizing the time, I just want to thank the co-authors or collaborators that were involved with various aspects of the projects that led to this talk today. Thank you for your time.
Thank you. And I noticed in the chat, it is nice seeing someone pronounce Poisson correctly, which I still can't do despite Asme helping me on Twitter. Thank you for pronouncing that correctly, because that was awesome. And like I said, I was saying earlier, that's my favorite distribution. So I love seeing this talk. Really spoke to me a lot. And there's a nice, got a lot of old-fashioned statistics in there. You know, the Census Bureau, I think as a conference full of data people, we can all say how much we love and respect the Census Bureau and the great things they offer to this country for over 200 years now, giving us this, not just the decennial census, but the rolling ACS is so valuable as statisticians. I think we should all, be very thankful and go thank Kimberly for not just Kimberly, but the whole Census Bureau for this. But everyone tag Kimberly on Twitter because that was awesome. All right. So now we come to